So in the previous lecture, we introduced the idea of electric current, and electric current is the rate of change of charge, and current density, which is basically the current per cross-sectional area. Now, these concepts are actually pretty well defined and are frequently discussed in beginning electronics classes. So you take a circuits class, you define this, but often they don't go into microscopically what's going on. They just simply state that this is what you've got. So what we're going to do in physics, though, is we're going to say, okay, let's imagine here that we've got a conductor. And so we have this conductor, and we are defining our conductor here, and we say, okay, so I'm going to apply an electric field here, and what's going to happen is the electrons, or whatever it is that's making electric current, starts moving that way. Now, we normally talk about in conductors that an electrical conductor is something that has free electrons that are free to move. So in other words, the outermost electrons, what we call the valence electrons, are not necessarily bound to any one atom, but they're shared by the material. And so you apply an electric field and the electrons start moving. That's not the only way you get electric current. You can get electric current in an entirely different fashion. For example, we could have a vat or a fish tank or aquarium filled with a fluid that has ionic molecules in here. And so each little ion is positively charged. And if I apply an electric field this way, then all those positive charges start moving that way. In that case, the current is in that direction, the direction that the charges are moving. In the upper case, the electrons are all moving to the left, and so the current is to the right. Okay, remember, electrons are negatively charged. Current is defined as positive charge. Okay, so there's more than one way of getting electric flow. So let's imagine here that we want to define this in some fashion. So we know that the current is going to be dq dt. So it's the rate of change here. Okay. And so I want to know, what is the electric current? Well, if I apply an electric field here, then these things start moving. So the question is, how many charges are in there to move? So the number of charges that are available in this entire thing, the total charge that's available to move, it's not the total charge that exists, but the total charge that's available to move. Protons aren't going to move because they're too heavy. It's going to be the valence electrons. Not even all the electrons in the atom, just the ones that are free and available to move. And so that we define quantity lowercase n. This is the charge density. So the charge density is going to be the number of charges divided by the volume. So this is the number of available charges to move. So times volume. Well, volume will be area times length. Okay, or I can call the length x. So this is A times x. So that's what we got available right there. Okay. Now it's the number of charges, but that's the number of charges, the charge density. We have to also multiply by the charge per carrier. Okay. Now, if we're talking about electrical conductor, then that is going to be the fundamental charge. So that would be the charge of each one of these little charges. That's an electron. So that's going to be it. Now again, we'll take absolute value because we know what direction things are going. So the Q that's available to move is going to be equal to N times X times A times E. So dq dt, that's going to be the current. Well, charge density doesn't change. Cross-sectional area doesn't change. The charge per carrier doesn't change, so it becomes dx dt. Well, what is dx dt? We know from physics 1 that's some kind of velocity. So the current is going to be NAE times some kind of velocity. Now let me put a little d here. We're going to call this drift velocity. Now let me explain what drift velocity is. So we've got our conductor, and we have all these little charges that are in the conductor. And so all those little charges, all the electrons are free to move. Now, again, there's only the ones that are free to move. So we apply an electric field, and so what happens is they start accelerating this way. Remember, the electric force is Q times E. The electric force is MA, that's Q times E. So they're all going to start accelerating. So the acceleration is going to be QE over M. So they're all start accelerating. Well, the longer the electric field is in place, the more they accelerate, and so the faster they go. Well, not exactly. What happens is once they start accelerating, they bump into something and they rebound. They ricochet off of it. So that force then slows them down to their stop, and they start accelerating again, bounce off of something. And so they go and bounce off of something, go and then bounce off of something, go and bounce off of something. So what happens is they're constantly bouncing off of things. So what we do is we define an average velocity that we call the drift velocity. So that drift velocity is this average velocity in there. And in the current here that we define, the current is going to be N times A times E times the drift velocity. Okay, now the important thing here is the drift velocity is not the actual velocity the electrons are going, because the electrons can go up to very high speeds and then bounce off, go back, go high speeds, bounce off. So the actual speed of the electrons is not the same as the drift velocity speed. The drift velocity speed is the average speed. Okay, now that depends in part on the electric field. So that electric field is what defines that drift velocity speed. Okay, now how big is this drift velocity speed? Well, the drift velocity speed depends in part on the material, and it depends in part on the electric field. Now, the interesting thing is the drift velocity in copper can be as little as a centimeter per second. Okay, well, think about that. You turn on a light switch, and how many centimeters is it from the light switch until the light bulb? Well, obviously the light bulb doesn't shine unless there's current going through it. So you turn on the light switch, and it would take a very long time for those electrons to get there. We don't worry about that, because you turn on the switch, and then you have the light bulb. Well, when you turn on the switch, you're allowing the electric field to go through here, and there's already electrons in that wire, so they start moving with the electric field. And so you're not having to wait for the electrons to actually move. All you have to do is wait for that electric field to be established, and that happens extremely fast, at close to the speed of light. Well, the other thing that happens, though, is when electrical wiring in the house is actually AC, which means that it goes back and forth. The electric field goes back and forth 60 times a second. So how far do those electrons go in 1/60th of a second? Not very far at all. So that means you don't really get any electrons from the power company when you use AC. All they do is jiggle the electrons that are in your wires. Okay. So this is the basic definition of electric current based on what's going on microscopically. Now, if we want to deal with current density, then current density is going to be I over A. Well, we plug in what we just came up with for the current, which was NA E V sub D over A. The A's cancel, so J is going to be NE V sub D. Okay, so the current density is only determined by the density of charges, the charge of each thing that's moving, and the average drift velocity. So the average velocity. So now we're ready to start doing maybe a few numeric examples. You might question though, well, we said that J was a, so we can do that pretty easily here. N, E, V sub D, and we can talk about the actual vector of V. And again, this could be very, very small. You know, I mean, you know, again, it can be a very small number here in terms of this, but because you're not just getting in the electrons themselves, you're just moving all the electrons that are in the wire itself.